Hello everyone, I'm Shivani Goel. The title of my poster is Distribution of Generalized Ramanujan Sum. It is based on the joint work with my advisor Dr. Sneha Chaubey. So I'll start with the definition of the Ramanujan sum. So this sum was first introduced by Srinivasa Ramanujan in 1918. So if we denote it by CNM, it is nothing but the sum of nth primitive root of unity, which we can write in the with the use of Mobius function given by this. So we can see the Ramanujan sum in almost every field of mathematics, and there are many applications of Ramanujan sum. Like it is used in the pairing type formula, in the distribution of rational number in the short interval, in the proof of Vinogradov theorem, and many more. Other than this, it is used to identify the periodicities of signals and extracting the periodic component. If one use Ramanujan Fourier transform, instead of discrete Fourier transform, it gives more efficient signal periodicity. So here is the graph for RIP normalized symmetry of Mobius function. So we are interested in the generalization of Ramanujan sum. There are many generalization of Ramanujan sum like Cohen Ramanujan sum, Anderson-Pustel sum, polynomial Ramanujan sum, and Ramanujan sum over number field. So if K is any number field and I and J are the non-zero integral ideal of its ring of integer OK, then the Ramanujan sum is the analog of second definition of Ramanujan sum in terms of Mobius function. Here Ni is the norm of the ideal I and mu I is the generalization of Mobius function over number field. And if we see that if K is equal to 2, the sum is coincide with the usual Ramanujan sum. So this is the definition and brief motivation to study the Ramanujan sum. Now we come to the objective of this poster. So we are interested to find this sum. This is basically average of the moment of Ramanujan sum. This sum was first considered by Chen and Kumchev for the usual Ramanujan sum. They found this sum when they were trying to find the definite approximation of PLs by sum of rational numbers. And they proved this result for m is equal to 1 and 2. So basically first and second moment. Later, using the similar technique, Robles and Roy proved the first, second, and higher moment for the Cohen-Ramanujan sum, although their result for higher moment is not correct. With regards to number field, the sum was first considered by Nowak, where he showed that that the first moment is approximately is asymptotically equal to rho ky, where rho ky is given by this. Or we can say that rho ky is the residue of Dedekind zeta function at s is equal to 1. So we are interested in basically is the second moment when m is equal to 2. So we prove that. So these are main result. First result is for proofer domain. So proofer domain is a special kind of domain where we satisfy the property that the norm of any of its two ideals is equal to the norm of their LCM times norm of their GCD. So if we consider this condition that norm of ideal is less than equal to y, number of that ideal is equal to this, then we'll get the second moment is equal to this, provided that x to the power lambda is less than y for some lambda greater than 1. So we consider the proof of this theorem. So we prove this theorem by some elementary number theory. We just change the order of summation, then we'll get this sum. And now use the property that the norm and upon LCM is equal to GCD of proofer domain. This will give GCD, and then do the simple calculation, we'll get the required result. Our second result is for the quadratic number field. So when y is between x and x square, the second moment is given by this sum. And for y is between x square and x cube, second moment is equal to this. So to prove this theorem, we need some preliminary. First is the Perron formula, which gives us a relation between the average of a function and its Dirichlet series, where Dirichlet series is equal to this and given by this. Second is the Dirichlet series of the function Cji, which is equal to this, the generalized divisor function over delta and zeta function. And third is the key lemma, which is the average of the divisor function given by this, where the main term is given by this and this error term. Now we are ready to prove this theorem. So first we use the Dirichlet series, which will give this sum, and now we square this sum. So we'll get this integral plus the error term of the order x square log y and the divisor function. Now we'll take the summation over I. Since these sums in this integral, there are only two functions which dependent on I. So, and this integral is absolutely convergent. So we'll take summation inside the integral and use the lemma. After that, we'll use these bound for direct kind function to find this integral, and we'll get the required result. Here are some future directions. Like one can consider the higher moment for usual Ramanujan sum and improve the result for number field that we have. One can consider the Ramanujan expansion for number field, and also one can find the distribution of Ramanujan sum over function field. Here are some references that we used. Thank you.